Good evening. I think this is the last class of Anova. So, in my previous class, yes, following good evening. In my previous class, I discussed orthogonal polynomial. The definition of orthogonal polynomial is as follows. Suppose yi can be written as alpha naught xi naught xi alpha 1 xi 1 xi plus alpha p xi pxi plus ei, where psi I x is a polynomial of degree I is I run from 0, 1 to up to p, which are mutually orthogonal. So that is psi I xi j x xi k a equal to 0 if j not equal to k, and this is equal to j squared xi if j equal to k. Okay, so this is the definition of orthogonal polynomial. So actually, when if we take polynomial, it is better to use orthogonal polynomial so that we can easily get estimates of this. How? Then in matrix notation, the module is one can be written as expectation of y current, which is equal to xi alpha curve, where and dispersion of y curve, this is equal to sigma square I, and alpha curve, this is the this is nothing but alpha naught alpha 1 up to alpha p is the vector of the new p minus 1 parameters and functions of the original betas in polynomial. This is come from the polynomial regression, that is related to the original beta in. If you assume the equation expectation y given x, which is equal to beta naught beta 1 x beta 2 x square beta p xp, and this xi is the matrix coefficient of coefficients xi x xi xi with orthogonality property. That is, sum over I from 1 to n xi j xi xi k xi, sorry, xi xi j xi, which is equal to 0 if j not equal to k, and this is diagonal elements are I from 1 to j, sorry, I from 1 to n xi j square xi. If j equal to k, so this should be x. This implies xi prime xi, this is a diagonal matrix, hence xi prime xi whole inverse is also diagonal. When the diagonal elements are of xi prime xi inverse are 1 by this sum over I from 1 to n xi j square xi then we get using Euler's estimation. So this is equal to alpha curl hat which is equal to xi prime xi inverse xi prime capital Y. So it's equal to, this is obtained from least square technique. This is this is obtained from normal equations of least square technique. So it's equal to, this imply alpha hat, which is equal to sum over I from 1 to n psi j xi, and it should be alpha j di j xi yi by sum over I from 1 to n xi j xi square. Okay, and variance of alpha j hat, which is simply sigma square I from 1 to n xi j square xi. So please check, this is your another one. And covariance, since yi's are independent, covariance alpha j hat alpha k hat equal to 0 if j not equal to k. Similarly, you can find SSE sum square dp error. Please check, this is your another homework, which is equal to y prime y alpha curl prime y curl y curl xi y curl. You get, if you simplify, then you get this form. Alpha j hat square sum over I from 1 to n xi j square xi, and its degrees of freedom n minus p minus 1. The practical advantage are, practical advantage are the values of alpha j hat and variance of alpha j hat depend only on the polynomial X occurring with alpha j in module yi alpha naught xi naught xi alpha 1 xi 1 xi alpha p xi p xi. Plus ei. So after if after fitting an orthogonal polynomial of degree p we want to add one more term alpha p plus 1 xi p plus 1 x, then we are not to change the values of alpha hat terms already obtained while fitting a pth degree polynomial. We only obtain the estimate of the parameter alpha p plus 1 introduced by the additional term in the module, namely alpha hat p plus 1, this is equal to sum over I yi xi p plus 1 xi by sum over I xi p plus 1 xi square. Similarly, the variance of alpha hat p plus 1, which is equal to sigma square I from 1 to n xi p plus 1 square xi. And new residuals SS, new residual SS is SSE, sum of square due to error, is equal to sum over I from 1 to n yi square minus j from 0 to p plus 1 sum over I yi by j xi square divided by sum over I xi xi square with df n minus p minus 2, which is the residual SS after fitting a eighth degree polynomial. Minus the SS due to alpha hat p minus 1, p plus 1. I mean to say this SSC p, which I already computed for p degree polynomial, minus just this one, sum over I yi xi p plus 1 xi square by sum over I xi j square xi. Xi p plus 1, sorry, xi p plus 1 xi. Okay, just take that. So, if you consider only polynomial, then you need to, every time when you are adding a new degree, then every time you need to fit whole polynomial. But here, we see that if you add one more, or increase 1 degree, then you just compute the last adding piece. Okay, so this is the beauty of this. If you use orthogonal polynomial, just compute additional part. You do not require to compute whole things. Okay. So as we have already mentioned, the above features of the orthogonal regression, model facilitate the fitting of a polynomial equation by increasing the degree of polynomial regression degree of polynomial step by step, and judging the improvement by computing SSE at each stage. The computational is not possible is not possible with non-orthogonal regression model. Where with each additional term all the previous coefficient will change and the SSE will also need to calculate accuracy. So this is the advantage of orthogonal polynomial. Okay. Next, we want to test for multiple linear regression model. Let us suppose that we have a set of k independent variables say x1, x2, xk, and dependent variable y, and the model we take yi equal to alpha plus beta 1 x1I, beta 2 x2I, beta k xki plus epsilon I, denoted by equation 1, I from 1 to n, where epsilon I are IID normal 0 sigma is. We are interested in the null hypothesis. H not all beta j equal to 0. This means there is no dependence of y on k fixed variables x1, x2, x3. And one more thing here I want to mention, that is sigma square is unknown. Okay. For simplifying the the determination of the least square estimates of the constant alpha and beta j, we can write the above model equation that is 1 as yi alpha hat beta 1 x1I dash beta 2 x2i dash beta k xki dash plus epsilon I, where x ji dash is equal to xji minus xi xj bar. Now applying by an application of better to write in that. Suppose I define s1 square, which is minimum over sum over I yi minus alpha dash beta 1 x1 I dash beta 2 x2 I dash, sorry, minus, okay, so beta k xki dash whole square, and this is equal to sum over I yi minus y bar whole square. If you use the least square estimate of alpha betas, then you get, since in this topic I several times discussed the least square estimate, so I just skip those portion and write the estimate of least square estimate of alpha dash beta 1 beta 2 beta 2. Okay, so use this, you can get is equal to beta j pj is degrees of freedom n minus k minus 1, and where this pj is equal to sum over I from 1 to n xji minus xj bar yi. So this is your homework. Just use the square technique of alpha dash beta 2 beta k, or you can minimize this portion, okay, with respect to alpha dash beta 1 beta 2 beta k, you get a least square estimates. Use this square estimate, get this part. So this is your homework. This part is your homework. Okay, please check this one square and immediately next this. So please submit homework. You know that there is the internal marking. Okay, depending on your assignment. So do not forget this. Otherwise, you may penalized for that. So beta j is the least square estimate of beta j, and h2 square is defined as minimum over alpha dash beta. So it is better to write minimum over alpha dash and beta 1 beta. So this is minimum minimized with respect to alpha dash beta 1 beta k. Similarly, here we also minimize this beta 1, the alpha dash beta 1 beta k. Another restriction, that is subject to the conditions, subject to the condition beta k, subject to the condition h0. Okay, so now this is sum over I yi minus alpha dash beta 1 x1 I dash beta k xki dash whole square. And under this condition, this should be yi minus y bar whole square. So this is your another homework. Okay. So thus, I know Polomi we have submit, but is you can tell your friend, those who not attend class regularly, they submit. I will inform you. Okay, so please submit your assignment. I will inform you within time. Okay, I got your one assignment, that is Anova. Okay, but there are several assignment or homework. I already mentioned in my during my class, just homework. So please do all this thing and then submit again if you miss something. Otherwise, you should be penalized. Please tell your friend, those who are not attending class regularly, please tell them they submit assignment before ending this month. That is, the last date is 31st July. Please submit your assignment within 31st July. Otherwise, I cannot entertain you. So thus, I know I already I have already seen these two assignments. Okay, so please submit if there is anything is missed. Okay, I didn't find time to check your assignment thoroughly, but I see you have submit two assignment, and I definitely go through. I will definitely go through it, and I will. If there is any difficulty, then I will definitely contact you. But if in meantime you should check if you have any, if you miss any assignment, and if you miss, then do it and submit, and also submit assignment of this class also. Okay, so up to that day you submit all the assignment. So please check this is, and the degrees of freedom is equal to, follow me, I am telling you, please tell your friend, those who do not attend class regularly, they submit their assignment before 31st July. Otherwise, they penalized. Okay. Okay, thank you, Polomi. I will check. I knew you have submitted something. I see you send me a mail. I already observed this thing, but I am telling you, I request you, please tell your other friend, those who do not attend class regularly, please tell them they submit their assignment before 31st July. Otherwise, they penalized. Okay, because you know you have a 20 marks internal marks for assignment, so please take it seriously. Thank you, Pauline. So the degrees of freedom, that is n minus 1, thus s2 square minus s1 square is equal to sum over j from 1 to n bj, capital Pj. This is equal to ss due to multiple linear regression is equal to SSR A with degrees of freedom equal to K, and S1 square is SS due to error. We denote this by SSE, say. Hence, for our data, okay, thank you, Paravi. Okay, now you are fine. If so, please do it. Yeah, you have enough time. Now it is 19. I think you have 12 days. So please submit assignment within this due date. Okay. Thank you. Henceforth, hence, if for our data f equal to SSR by K, SSE by n minus K minus 1 greater than f alpha K n minus K minus 1. This is the upper alpha percentile point of f distribution with K n minus K minus 1 degrees of freedom. We reject H naught at level alpha. Okay. And the Anova table first column is source of variance, source of variation. So the first entry is due to multiple linear regression. Multiple regression, linear, then total. This is K n minus K minus 1. This is n minus 1. SS sum over Bj Pj sum over yi minus y bar whole square minus sum over j bj pj and sum over I yi minus y bar whole square. Okay. So this is for linear sum over I, yi, S is due to linearity is sum over I, yi minus y bar whole square minus sum over j bj pj, and this is for sum over sum of square due to multiple linear regression, that is sum over j bj pj. Okay, and this is SST. So ms is equal to ms r multiple regression due to multiple regression, that is equal to SSR, and you know this by SSR by K, and SSC, this is due to linear regression, which is equal to this is SSC, so it should be MSC, which is equal to SSC by n minus k minus 1, and last column, that is F, and F equal to MSR, this is F equal to MSR by MSC. So please write this here. Okay. A slightly different problem. In connection with multiple linear regression, is the following. Given a set of p plus q independent variables, one may want to know whether a particular group of q independent variables has any effects on the prediction of the dependent variable, after already having fitted the other p independent variable p independent variables and without any loss of generality, the former group of q variables may be taken to be the last q of the p plus q variables, then the null hypothesis is h naught beta p plus 1 beta p plus 2 beta p plus q equal to 0. The linear model in this context is yi alpha plus beta 1 x1i beta 2 x2i beta p xpi plus beta p plus 1 xp plus 1i beta p plus q xp plus qi plus epsilon I. Also, you can check this x1 square, which is written as you define s1 square same way, that is, this is minimized, the error term is minimized with respect to sum of square root error, minimized with respect to alpha beta 1 to beta p plus q. So this is again same as yi minus y bar whole square minus sum over j from 1 to p plus q bj, capital Pj, with degrees of freedom n minus p minus n minus p minus q minus 1, okay, and Pj equal to sum over xji minus xj bar whole xj bar into yi I from 1 to small u. And similarly, you can define x2 square, which is I from 1 to n yi minus y bar whole square minus sum over, since this is under h naught, so is j from 1 to p, sorry, q, no, is correct, up to p bj pj, okay, with degrees of freedom n minus p minus 1, okay. So now s2 square, similarly s2 square minus s1 square is equal to sum over j from p plus 1, is better to write bj star. These are not same thing. These bj stars are not same thing. Okay. So this is equal to j from 1 to p plus 1, j power plus 1 to p bj pj minus j from 1 to p plus 1 q bj capital Pj. 2 degrees of freedom equal to q. Here bj are the least square estimates of beta j for the model this. I denote this by 2 for model 2. And bj star are the least square estimate of beta j for the restricted model that is yi under h naught, the model under h naught, that is yi equal to alpha plus beta 1 x1 I, beta 2 x2 I plus beta p xpi 7. Okay. Hence, h naught is rejected at level alpha if the statistics f, which is equal to s2 square minus s1 square, that is this divided by s1 square, this is into n minus p minus q minus 1 by n minus n by q, okay, by q, greater than f alpha q n minus p minus q minus, okay. Anova table first is source of variation due to multiple regression of y on x1, x2, xp due to multiple linear regression of y on xp plus 1 to xp plus q after fitting x1, x2, xp, and this is this is so this is due to multiple linear regression of y on x1, x2, xp plus q, and then error, then total. And degrees of freedom, it is p, this is q, this is p plus q, this is n minus p minus q minus 1, and this is n minus 1. It says sum over bj, capital Pj, j from 1 to p, this is j from 1 to p, bj pj minus j from 1 to p plus 1, p plus q, bj pj, this is s2 square, sorry, this is s1 square, and this is, no, actually this is, to subtract this, get after adding these two, we get j from 1 to p plus q, bj pj, this is star, so please rectify this should be v star. Okay, so this is equal to this, and this is s1 square, and last one is sum over I in yi minus y bar whole square. MS due to regression periodic degree polynomial, NS due to periodic degree polynomial when already periodic degree polynomial is fitted. This is p plus ms r, p plus periodic degree polynomial. This is MSE, and F is F equal to MSR Q plus Q given P, MSR Q given P by MSE. MSR Q given P by MSE is a F ratio. Okay. The hypothesis that will be considered next under multiple linear regression model is the following, that is H naught beta j equal to constant C for any particular j and C being any given value including 0. For this, we refer to the normal equation for estimating the beta I, beta j, which can be written in the matrix notation a beta curve, capital P curve, where capital A, which is equal to ijth element is jz as element, capital to say jz equal to x j I x j prime I, which is the I j j dash element, and the order of A is k cross k since we have k betas, and beta curl, which is equal to beta 1, beta 2, beta k, and capital P, this is equal to P1, P2, Pk with Pi, which is equal to sum over I from 1 to n, it is Pg, okay, not Pi. It's Ji yi, and beta curl, then beta curl hat, which is equal to A inverse capital P, and we can if you find this from beta j hat, you see that beta j hat is a linear function of independent yi's, and since yi's are normally distributed independently and beta j hat is a linear function of independent yi's, then from the property of normal distribution we can say that beta j follow normal distribution with mean equal to beta j, and variance of beta j hat, which is the jjth element of a inverse, which is written as C jj sigma square, and covariance of beta j hat, beta j dash hat, which is the j dash element of A inverse, where we denote the A inverse by capital C and the ijth element of capital C, Cij. Okay. So for testing H naught, beta j equal to C is C, the test statistics T, which is beta j hat minus C by this is better to write C naught, otherwise this small c and capital C you cannot distinguish here. C naught, okay. So it is better to write C naught. So C naught, beta j hat minus C naught, standard error, because sigma square is unknown and it is estimated by MSC. So MSC into Cjj. And it follows T distribution with n minus k degrees of freedom under H naught. So we reject H naught at level alpha if T greater than mod T greater than T alpha by 2 n minus k minus 1 for two tail test. And for right tail test it should be T greater than alpha n minus k minus 1, and for left tail test then T should be less than minus T alpha by T alpha n minus k minus 1. Repeat again. For right, this is for both tail test mod T greater than T alpha by 2 n minus k minus 1. For right tail test it should be T greater than T alpha n minus k minus 1. And for left tail test, T less than minus T alpha n minus k minus 1, where T gamma n minus k minus 1, you know the upper gamma percentile point of T distribution with n minus k minus 1 degrees of freedom. Okay. So now if you want to test H naught, beta j prime, then similarly you can define the test statistics, and again it is a T which is equal to beta j minus beta j prime root over Cjj minus 2Cj dash j dash plus Cj dash j dash minus 2 into j dash, okay, into MSC. So this is your homework. Please check it is the test statistics for testing H naught beta j dash. So for this you need to find expectation beta j hat minus beta j hat dash, then find variance of beta j hat minus beta j dash hat. Then from this you can say that this is a T distribution. Before that you need to check whether beta j hat minus beta j dash hat the linear function of independent YIS. Then from the property of normal distribution, before you can say that this follows beta j hat minus beta j dash hat follows normal distribution, which means 0 with variance Cj j dash minus 2 Cj j dash into sigma square. Okay, and since sigma square is unknown, then you get this statistics. This is T statistics under regression. This follows T distribution with n minus k minus 1 degrees of freedom under H naught. Okay, we reject H naught if at level alpha, if mod t greater than T alpha by 2, n minus k minus 1. This is for both tail test. This is for both tail test. For two tail test, for one tail test, that is for if you consider right tail test, that is beta j greater than beta j dash. This should be T greater than T alpha n minus k minus 1. For left tail test, that is beta j less than beta j dash, then T less than minus T alpha n minus k minus 1. Okay. Now we consider the last portion, that is effects of violation of the assumptions made in the analysis of variance. The assumptions, the underlying assumptions for analysis of covariance, analysis of variance are normality of the error and also of the random effects and secondly independent of errors independence of errors and lastly we assume equal variance, that is homoscedasticity of errors. Homo HOMO SCEASTICT, homoscedasticity of errors. In model 1, the normality assumptions is needed only for, this is a fixed effect model, okay, needed only for hypothesis testing and interval estimation. Thus, all points estimators and their estimated variance variances remain invalid even under sorry remain valid even under normality. Heteroscedasticity and correlation error of errors do not bias the estimator. For other models, too, the estimator of variance component remain unbiased even the non-normal random effect, even with non-normal random effects. Okay, so please tell me, can I rub the right hand portion? Please tell me, can I rub the right hand portion? So I think it is better if you write model 1 instead of fixed effect. Fixed effect. Okay, thank you, follow me. In fixed effect model, instead of model 1, you write fixed effect model. The normality assumption is used for hypothesis testing and interval estimation. Thus, all point estimators and their estimated variance remain invalid even under normality. Non-normality, heteroscedasticity and correlation errors do not bias the estimators. For other models too, the estimators of variance component, other models is random effect and mixed effect. Estimators of variance component remain unbiased even with non-normal random effect. Okay. So robustness against non-normal normality of the test on means and the lack of it in the case of test on variances lead us to expect that test and confidence interval in case of model 1, that is fixed effect model, in the case of fixed effect model, will be robust to non-normality while those in other models, that is for random and mixed model, which are mainly concerned with variances, will not be robust. Investigation have shown that the effects of heteroscedasticity which are large in the case of fixed effect model, effects model can be reduced by using experiments with equal cell frequency. Okay, with equal cell frequencies. I think you mean second para. The robustness against non-normality of the test on means and the lack of it in the case of test on variances lead us to expect that test and confidence intervals in case of fixed effect model will be robust to non-normality, while those in the other models which are mainly concerned with variances will not be robust. Investigations have shown that the effects of heteroscedasticity, which are large in the case of fixed effects model, can be reduced by using experiments with equal cell frequencies. Investigation, the effects of stochastics, the effects of stochastics dependencies, stochastic dependence among the errors may completely vitiate the test as a remedy as a remedy the use of randomization should be taken into consideration while allocating the treatments to the different experimental units. To different experimental units. Experimental units. Transformation of the observations are often used to reduce non-normality or heteroscedasticity heteroscedasticity. The study of the robustness of the analysis of variance methods has led to has led to has led to the search for non-parametric methods for analysis of variance. Such non-parametric methods for such non-parametric methods exist and are completely robust for any continuous distribution, for any continuous distribution, and compare favorable with the classical normal theory procedure. Classical normal theory procedures. And this is The name of this non-parametric methods is Kruskal-Wallis one-way Anova. Kruskal-Wallis one-way analysis of variance, and this is based on ranks. So this is not our considerations, because here I only consider parametric method, that is Anova, based on normality assumptions. So I want to stop here. This is the last class. Hope you enjoy the all the classes based on the analysis of variance, and we will come with a new topic very soon. So please stay with us. Thank you. So please tell me, have you any queries regarding this? Otherwise, I end this stream. So thank you and all the best. Thank you. And all the best. Please stay with us. We will come with new topic. Hope you enjoy. So, have you any queries and questions? Please tell me. I will answer you. Okay, thank you, Polumi. Thank you. So please tell your friends to submit all the assignment before 31st. Probably take care of your health and try to finish within time. If you have any difficulty, please call me, or you can mail me also. Thank you. So, can I end the stream? Please tell me. Okay, thank you everybody, thank you.